Okay, this is the last part of this module. It is concerned with electrical drives. Now, if you think about electric vehicles or hybrid electric vehicles, wheels are driven by electric motors. And therefore, electric motors are an essential part of an electric vehicle. Without these, then you don't have the power source to drive the car forward. Okay. Now, there are many different types of electric motors. Now, ones I listed here are just some of the very commonly used electrical machines. Okay, so in this lecture, or under this module, I'm going to explain the general principles of all four different types of motors listed on this slide, but I'm going to actually focus a bit more on the first one, the brushed DC motors, and also the last one, AC induction motors. The other two are very similar, but I'm just going to explain the principle fairly briefly. So first of all, let's talk about the brushed DC motors. Now, it's funny now we add a word brushed to the front of DC motors. In the olden days, we didn't really have to because before the age of power electronics, DC motors had only sort of one type, just brushed. Okay, the brushness, the second one on my list, the brushness only existed after we had better means of control motors with power electronics. The brushness is actually a type of AC motors, although they are called DC, but they're just controller-like DC motor. Okay, so the real DC motor is the ones that with brushes. Okay, now brush machines consist of several key parts. First of all, you have the stators, or the stator for the motor. Stator is a part of the motor that doesn't move or doesn't rotate. On the stator of a DC motor, or brushed DC motor, you will have pairs of magnets. Now on this diagram, I only show you one pair, but it's possible to have more than one pair. Okay, just to make the operation more smoother. One pair is enough to illustrate the principle of the operations. Now the pair of the magnets can be made of permanent magnets, or they can be made of the coils with what we call field windings to produce electric field. So that's why they call it field windings. So that's a stator. Then there's a moving part. That's the part that rotates. And this is called a rotor. On a rotor, you have coils as well. This coil is called armature winding. Okay. Now the armature winding is connected to the power source through commutators and brushes. I'll explain that in a minute. Okay. This part is called commutators. This part is called brush, and the voltage is fed through the brush to the commutator and to the armature winding. Okay, so the current, say for example, the current goes in from here, goes through this side, which you don't quite see, and then comes back from this side and then goes out. Okay, now the interaction between this current in the field winding and the magnetic field produced by the magnets on the stator, or the magnetic field on this produced by the magnets, or the field winding on the magnet. When they interact, it produces forces. Okay, so for example, on this side, on the near side, the force is coming down because of that interaction between the magnetic field and current. On the other side, because the current is flowing in the opposite direction in the magnetic field, one is going away, the other one is coming back. Okay, so the force will be in the opposite direction. So when this side going down, this side going up. Now, one side is going up, the other side is going down. That causes a rotational torque. So that's what the driving effort make the rotor rotate. Okay, so that's basically how it works. Okay, now of course, as the rotor rotates, the armature winding rotates with it, and it changes. So at some point, if I just go back, at some point, this side goes up, this side goes up, this side goes down, and they comes back because I'm ignoring all the other possible pairs of windings and also other fields. Just ignore that bit. This side moves up, this side moves down. Eventually, they will move out of the magnetic field produced by this. But as I said before, we have more than one armature coil on this stator. So they are positioned in different angles. So the next coil will come into that magnetic field and produces force that will continue to rotate the stator. Okay, but eventually this pair, if you just imagine this pair will be pushed, and along the angles. Okay, eventually this side will come to that side, and that side will move to the opposite side. Now, if that happens, okay, then you will need to change the direction because we don't want this current going this way. Otherwise, it will produce the opposite force. Okay, this current will need to reverse direction. Okay, the direction is reversed by using the commutators and the brushes. Okay, so if you look at this side is connected to that block of the commutator, and this side of the coil is connected to this part of the block of the commutator. But brush are not moved. Okay, and the polarity of the power source is not changed. So when you turn around by 360 degrees, B comes to A comes to B. Therefore, the current going to B will be supplied by the positive power source. Therefore, and the A side is going to be supplied by the brush on the negative side. Therefore, the current is reversed. The current is reversed. Therefore, the force will be continued in the same direction as before. Okay, so there is constant swapping of the opposite sides of the coils because we have more than one coils and they are positioned in different angles. They continue to come to the interact with the magnetic field, and they continue to produce the torque needed to rotate the machine. But that brush itself is problematic because there has to be contact. The brush has to be in close contact with the commutators. Okay? So one of the problem is it wears off because of frictions, but also you're changing the direction of the current as they rotate, get into contact as well. Okay, so this side has to change from all of a sudden from positive to negative, the other side from negative to positive, and it causes something called electrical arc. Okay, that all can cause other damages to the commutators and brushes. I expand the commutators. Oh, I don't know why there are two slides. Yeah, well, as I already explained here, you have different segments, different set of these armature coils come into that will produce the forces. But I already explained, so I'm going to skip that part. Now, you need two parts of an inertial machine for the inertial machine to work: the rotor, with the armature winding, the stator with the permanent magnet, or with electrical coils called field winding. And if you use field winding rather than permanent magnets, then there are different ways to control the electrical motors or the DC brushed motors. You can actually connect the two fields, the armature winding and the field windings, connect them in series, or you connect them in parallel, they call shunt windings, or you can connect them in a compound configuration, part series, part parallel. But the most flexible way to control a brushed DC motor is to use separate excited windings. Okay, so the power source for the armature winding is different from the power source of the field winding. Okay, that will give you the maximum flexibility to control the DC motors. So I'm going to use the equivalent circuit to explain how the separately excited motor work. So on the right hand side, we have two parts of a circuit diagram. Okay, so this part, the left part, represents the field winding. The right hand side represents the armature winding, or the equivalent circuit of the armature winding. So a voltage is applied to the field winding, and therefore the current is fairly straightforward because the voltage is going to be a constant. It's a DC voltage at different adjustable levels. Therefore, the current simply equals to Vf divided by Rf. Rf is the resistance of the field winding. So you produce a current, that current in turn produces the magnetic field in the motor. On the other side, a voltage Vt is supplied to the armature winding. Armature winding will have its own resistance, but there's also something called back EMF. This part is known as the back EMF. It's a result of the interaction between the magnetic field and the movement of the rotation of the rotor. Now this is actually produces a voltage that opposes this voltage. So it's trying to reduce the current in the coil. Okay, so bear that in mind. One other thing that you need to be careful is that when we control the field current, in general, when the current is small, the magnetic field produced by the field winding approximately has a linear relationship with the current. But as the current increases, the magnetic field tends to increase slower, but eventually it flattens out because the saturation effect in the stator. Okay, so there's a really, when the current is fairly, when the current goes above a certain level, you have a nonlinear relationship between the field current RF and the magnetic field it produces. And other thing you need to perhaps bear in mind is that in an arrangement like that, the current in the armature winding, on the rotor, RA, tend to be a lot greater. Okay, it carry most of the current, whereas the current required to produce a magnetic field is very relatively small, partly because of the saturation of the flux. Okay, so we have this equivalent circuit, and we have this relationship as well. Current equals to VF over IF. That's the current needed to produce the magnetic field. That's equation 1. Equation 2 gives you the formula to calculate the current in the armature winding. Okay, now because the voltage VT is supplied from outside through the brush, EA here is a voltage produced due to the back EMF effect. And so the difference between the two divided by R, the resistance of the armature winding, gives you the current, or gives you the armature current. Okay, so this is how the two currents are calculated. Back EMF is related to three things. The KE here is the back EMF constant. It is sort of a parameter that dependent on the actual design of a particular motor. So if the motor is designed, or if you buy a motor, then it will have a fixed value for the back EMF constant. Phi is a magnetic field produced by the field winding, or the stator. Omega is the angular speed of the motor. Okay, so you can see that if, for example, if we fix the field, magnetic field, say if we're not changing IF, therefore the phi is a constant, KE is also constant, then the back EMF is actually proportional to the motor speed. So the higher the speed of the motor, the higher the back EMF. Now, if I look back at that equation, that means to maintain the same current, then you will need a higher input voltage. If the input voltage for the armature winding is not going up, then the current will come down. So if you fix a supply voltage, then the current will go down in the armature winding. Now, as the current goes down, that affects the torque produced by motor. This formula there, equation number 1, is the formula that we need to calculate the torque produced by electric motor. Now, before we go explain this one, I want you to have a look of the diagram on the right hand side. Now, because in my explanation for the production of the forces and the torque, I only use one pair of the magnet, and also I use one coil for the armature winding as well. But in reality, you could have a lot more than single pair or single winding. So in this diagram, I have 2 pairs of magnetic field. So there's north, there's south, there's north, there's south. So they're actually physically, mechanically, they're not opposed to the opposite to each other. So actually, So this magnet, for example, will work with this south, this north will work with this south, and this south, and this north will work with this south, and a part of that south, and vice versa. Okay, so the magnetic field flux goes through this way, and it goes through that way, and it goes through this way, and it goes that way. But also, this little circle there, each of that represent one armature winding, because you are looking at the motor from the side. So really you are looking at the cross section of the winding. So there's a lot more windings here, or winding pairs here, and they go through the two pairs of magnetic field to give you to produce its forces. Now, how many pairs we have? Obviously, pairs of magnets we have on the stator obviously affect how the force is produced or how the torque is produced, and how many armature windings we have will also affect how much torque and how much and the shape of the torque produced in the induction motor. Okay, so in this formula, the torque is actually equals to Km, which is a torque constant, times the magnetic field times current. So obviously, you can adjust the magnetic field to control the torque up to a limit, because after certain value, above certain value, it's going to saturate. And you can adjust the current in the armature winding to control the current. Again, that's also up to a limit, because you would have a limit on the current. Too much current will produce too much heat. Then you have a lot of losses, and the temperature in the motor can become too high. Km is a design parameter for a particular motor. So if you buy any motor off the shelf, or if somebody design motor, once its motor is designed, then Km is fixed. Typically Km, the torque constant, and Ke, the other one that I refer to. So, yeah, Km and Ke, that's the back EMF constant. They have in general, they have same values. But sometimes people can change the design to deliberately to make them different. Okay. Now, if I substitute, now I have a torque relationship Q equation number 1. If I substitute the current on one of the slide pages here, if I substitute this into I there, then I get K times phi, that's a magnetic field produced by field winding. This is the overall current. So actually I can calculate the torque from the voltage supplied to the armature winding and the motor speed and a magnetic field of the motor. Okay, so that would be the equation given here. So if you know the voltage, you don't really need to find out the current first and the speed. One of the things you could also note, or people often quote on a data sheet for an actual machine, is a starting torque. Starting torque is a torque that produces when the speed is 0. Okay, so that's just before the motor starts to rotate. So if you look at that formula here, when speed is 0, therefore omega is 0. So that second term disappears. That will leave you with equation number 2. That's K phi times Vt of R. That's when you have a much higher torque for a given voltage supplied to the armature winding. Okay, so as the motor starts to rotate, then this term becomes larger and larger. Therefore, current gets smaller and the torque gets smaller. Or you just, if you want to keep the same torque, you just have to increase the supply voltage as well as the omega or the speed goes up. But starting torque tends to be very, very high. Okay. If you apply a high voltage or the full rated voltage to there, and the current can be very high because there's no back EMF. So the VT over R that produces armature current that can be quite high or very high if this is a high voltage or rated voltage you apply. This current tends to be a lot higher than the rated current. The current level the machine can tolerate before it becomes too hot. So although it looks good, you have a higher starting torque, but that can only work for a very short time period. Okay, you will have to reduce that current down afterwards because otherwise produces too much heat in the machine, and the temperature will go up. Eventually, the machine will burn. The other thing that people can work out is for the maximum speed of the vehicle with no load. Okay. Now, with no load means we don't need any torque. There is no load, so therefore, this equals to 0. If that equals to 0, then Vt will equal to k phi omega, or omega equals to Vt divided by k phi. So for the rated voltage, if you use rated voltage and you use the standard field flux, then you will be able to work out the maximum speed of the DC motor. Okay, that's in an ideal case. The motor will not go above that unless you overdrive, unless you supply a voltage that you're not supposed to supply. So that is the general principle of that. So in my next lecture, I'm going to talk about other issues related to the brushed motors, DC motors.